does that work out? It comes from up here. We'll get more into this in chapter 10. I'm trying to give you a peek now. In one dimension, I can just write f times dx. I can do that in one dimension without specifying anything. Because in one dimension, what does it mean to be a vector anyway? So these are just numbers. However, in more than one dimension, force is a vector. Dx is a teeny little change in position. Dx is also a vector. Here I am multiplying two vectors together. If I multiply two vectors together, like in statics, an example where I multiplied two vectors together in statics was when I calculated the moment, I had to do product of the vector r times the vector f. I multiplied two vectors together in statics. I did not just leave it at that. I had to decide if I multiplied two vectors together, how I multiplied them together. So here when I calculated the moment, I did r cross f. The cross product is also called the vector product. Because if I do the cross product of two vectors, do I get a vector or a scalar? I get a vector. The moment is a vector. There's another option for multiplying vectors together. What's the other option we have for multiplying vectors together? Dot product. Does the dot product result in a vector or a scalar?
Scalar.
Scalar. In fact, sometimes it's called, instead of dot product, some people call it the scalar product, precisely because it results in a non-vector. So do you think this multiplication of two vectors, does that have to be a dot product or a cross product?
Depends on the situation.
Okay, for this situation right here, is energy a vector or a scalar?
Scalar.
So does that mean the work has to be a vector or a scalar?
Has to be scalar.
Has to be a scalar. So if I multiply two vectors together to get work, does that have to be a dot product or a cross product?
Dot product.
Has to be a dot product. Okay. It couldn't be a cross product. If it was a cross product, I'd get a vector. Okay. Now that's not an argument. There's more arguments why it should be a dot product and not a cross product. However, I can get there just on whether it's a vector or not alone. I can figure out that it has to be a dot product. Now for chapter 9, where I'm in one dimension, these aren't really truly vectors here. They only have one component, so you can treat them as numbers. So I can just be vague and leave it off. Okay? But it'd be better to think about that in the future. In fact, let's look at this v squared. 1/2 mv squared for kinetic energy. A v squared, what is that? Well, that's actually two vectors multiplied by each other. V squared is v times v, right? That's what we mean by v squared, a vector times a vector. When I do v squared, is that v cross v or v dot v? So, does that have to be a dot product or a cross product?
Dot.
It has to be a dot because kinetic energy is a scalar. So that v squared is really v dot v, if you're looking at this in terms of vectors. Just as one final review question before I do some examples of this. Suppose I have a vector A, and I do a cross product of A with itself. What do I get? I know I get a vector per se, but I mean, what?
0.
I get 0, yeah. Because the cross product is asking what component of the vector is perpendicular to that other vector. So A cross A is, what component of A is perpendicular to itself? None. So that's 0. Okay. So I've got these two relationships. They're useful for different kinds of problems. This one, work equals change in kinetic energy, is very useful when I'm working with forces and positions. Because here I have an integral of f dx. So if I'm working with forces and positions, and I'll do an example in a moment, this version is going to be more useful. On the other hand, if I'm working with times, here I have the integral of f dt, this version will be more useful. Okay, so example number 1. I take my marker, I drop it. So it falls 2 meters before it hits the floor. So I dropped it. It fell 2 meters before it hit the floor. So I'm telling you how far it went. And I'd like to know its velocity at the bottom. Could I do this using F equals ma? Yeah, of course we could. Would it take that long? No, it wouldn't. But let's do it this way instead. Let's use work equals change in kinetic energy. And I'm going to use work equals change in kinetic energy and not this version because I'm being given the distance of 2 meters. The marker falls for 2 meters, and I want to know how fast it's going after 2 meters. If I told you the marker falls for 2 seconds, how fast is it going after 2 seconds? I would use this version because it's involving time. My first question was the marker falls for 2 meters. How fast is it going after those 2 meters? All right, so let's try to use this relationship. So the work done, we use that saying, work done on something. This is the work done on the marker. So the work done on the marker equals the change in kinetic energy of the marker. What it does not say is the work done on the marker equals the change in kinetic energy of Fred. Okay, there's no such equation. It's the work done on the marker equals the change in kinetic energy of the marker. So this is the work done on the marker. This is the change in kinetic energy of the marker. What is the initial kinetic energy of the marker when I first let go? 0. Yep, because it's not moving. The final kinetic energy of the marker is 1/2 mv squared. What is the work done on the marker? Well, I need to go back to the integral of f dx. This f right here came from that f, that f, that f. When I write f equals ma, what I really mean is sum of all the forces equals m. I don't mean just pick one force that you feel like and use that force. I mean use all the forces added together. So when you use the work done on the marker, that force has to be the sum of all the forces acting on the marker. For this particular example, though, it's fairly straightforward. Can somebody, as it's going through the air, can someone identify one force acting on the marker? Gravity. If we ignore air drag, that's it, right? Okay, so let's ignore air drag from this first problem, and the force acting on the marker is going to be mg times dx. Okay. And that equals 1/2 mv squared. Mg is a constant. So the mg comes outside the integral. So mg times the integral of dx is 1/2 mv squared, or the integral of dx is the change in position. So if I'm going from x initial to x final, the integral of dx is x, which is that I put in the x final minus x initial, which gives me delta x. So mg delta x is 1/2 mv squared. Delta x is 2 meters, so I can cancel my m's, and I get g times 2 is v squared, where v is equal to the square root of 2g. You may have noticed I was a little reckless on one detail. I will now clean up that detail. My change in position as it fell, did the marker increase in position if I call that way up, or did it decrease in position? Decrease. So actually my change in position in this case is negative.
Really important question. How did that 1/2? Should it be 4x?
Thank you, 4. Thank you. James is pointing out I forgot that 1/2.
So it would be, yeah, okay.
Square root of 4g.
So could that be 2
change in position was actually negative. So I'd get the square root of negative 4g, which would give me an imaginary number, because my change in position was actually negative. So what else did I forget here, Sean?
Gravity's negative.
Yes. So actually, the force of gravity is also negative, which then makes that two negatives, which gives me a positive. So it turns out my change in position was negative, but my force of gravity was also negative. So I get a negative times a negative, which made a positive, and I get b is equal to the square root of 4g. Okay, let's now take this and throw the marker upwards. So I take a marker, I throw it upwards, and I throw it with an initial speed of 20 meters per second. 20 meters per second is roughly how many miles per hour? Just roughly. Good enough. Okay. It's about 40. Okay, but I like Eric's guess. So if you want to go from meters per second to miles per hour and you are only trying to get a rough answer, you can just double it. So 20 meters per second is about 40 miles an hour. How fast does a baseball pitcher, professional pitch a baseball, roughly? 90. So do you think it's plausible that I can throw it up at 40 miles an hour? Maybe. Okay. Or at least maybe
Let's
one of
see
you
how.
could. Okay. Right. It would still be a fairly fast throw. 40 miles an hour would be. I remember once when I was young, I went to at the Jersey Shore. They had like these, throw a ball and measure your speed things. So I remember giving it my all. Throwing the ball, and it's like 50. Being so disappointed. My professional sports career was over at that point. So can I still throw it at 40 now? I doubt it. Okay, but let's just say I can, or did, at some point. So I throw it up at 20 meters per second. I want to know how fast it's going after it's gone up by 1.5 meters. So if I let go here, 1.5 meters would be roughly the ceiling. So I want to know how fast is it going when it hits the ceiling. Go ahead and work that out real quick on your own.